Hello guys, in the previous video we talked about weak acids and we solved the sample problem on how to calculate the acid dissociation constant when we know the pH. Now in this video we need to calculate the pH from the acid dissociation constant. In our practice question we have a 0.1 molar solution of acetic acid which is CH3OOH. We know the K sub A at 25 degrees Celsius, and we need to calculate the pH. Well, the pH equals to a negative log of the hydrogen ion concentration at equilibrium, so we will have to figure out the hydrogen ion concentration there. First step is that we need to write the chemical equation for the ionization or dissociation equilibrium. And as you can see, I already have the Rice table already. So I'm going to write the equation right in there. We have acetic acid, which is CH3OOH, and this is aqueous, and it's going to dissociate into the H plus ion, which is also aqueous, right? We are losing this hydrogen here, plus the acetate ion, which is CH3OO minus aqueous. So I have the reaction and it's nicely balanced. Now I need to write out the equilibrium expression. So K sub A in this case equals to the concentration of my products, which is the H plus ion multiplied by the acetate ion, CH3OO minus, divided by the CH3OOH concentration or the acetic acid concentration. Now the next step is that we need to set up the Rice or ice table to determine the equilibrium concentrations as a function of the change. And we are going to call the change in this case X. So I know that I started with a 0.10 mole per liter solution of acetic acid. Now the question is how much H plus and CH3OO minus did I have at the beginning of my reaction? Well, I know that I had no acetate ions there, but we can think about the auto-ionization of water, and it's probably going to be a really small volume. We know that at pH 7, it's 1 times 10 to the negative 7th. So let's see how large our change will be and whether it's comparable with the hydrogen ion concentration from pure water. So for now, I'm going to put a 0 right here and assume that it is going to be a teeny tiny number that doesn't make any difference. So then the change in concentrations, while the ratio from the products to the reactants is 1 to 1 to 1. So the change for the acetic acid is going to be minus X, for H plus X, and for the acetate ion again plus X. Now the equilibrium concentrations for my products are going to be X and also X, but if I add the equilibrium concentration as 0.10 minus X, as you can look at the equilibrium expression, I would end up with a quadratic equation. Now I want to make my life easier and make some assumptions to actually not to have to solve a quadratic equation. And in this case, I'm going to assume that the change in concentration during this reaction is going to be so small. So my X is so tiny that 0.10 minus X will still approximately equal to 0.10. Okay, so this is an assumption that I'm going to make it easier to calculate the pH, but I'm going to check for its validity later. All right, so let's plug in the values into my equilibrium constant expression and let's solve for X, which is going to be our H plus concentration from which we can calculate the pH later. So here I know that X multiplied by X divided by 0.10 will equal to 1.8 times 10 to the negative 5, which is the K sub A given in my question. From here, I can solve for X. So x squared equals, right, x times x is x squared, equals to 0.10 multiplied by 1.8 times 10 to the negative fifth. And from here, x equals to the square root of 1.8 times 10 to the negative sixth, right? This multiplication from here. And if you do this calculation, you are going to end up with 1.3 times 10 to the negative 3, which is the hydrogen ion concentration. Now, my question is this value really negligible compared to my initial concentration of my acetic acid? Well, let's see. So 0.10 mole per liters is my initial concentration. If I subtract from it 0.0013 mole per liters, I will still end up getting 0.10 mole per liter at my equilibrium, right? So it makes sense that I made the assumption that my X is going to be a small volume. By the way, you can make this assumption if your K sub A, so the acid dissociation constant, is a small number, because I will know that when K sub A is a small number, I have a very weak acid which only very slightly dissociates, so my X is going to be a teeny tiny value. Okay, so from here I can simply calculate the pH, which is the last step. So pH equals the minus log of the H plus ion concentration, which is minus log of my X, right? 1.3 times 10 to the negative third. And if you do this calculation, you are going to end up with 2.87. So the pH of our 0.1 molar acetic acid solution at 25 degrees Celsius is 2.87. All right, I hope this makes sense. See you in the next video.